So I'm going to try to explain how we can determine whether or not two positions or two SNPs are linked. And the way to do that is, like, one thing you got to do is do a cross. So first of all, let's assume that these are two plants. And this plant, this first plant would have, let's say at position number 1, or SNP number 1, it would have, let's say, a T and a C. So it's diploid. So on one chromosome, it would have a T at this position and a C at that position. Because again, it's diploid, so there's 2 of every chromosome. So the corresponding plant, or the plant that's going to cross with, will have, let's say, at position number 1, a C and a C. So it's diploid again, so there would be a C here, and then there's going to be a C there. Yeah. At position number 2, in this plant, let's make it this an A and a G. We discovered that that's an A and a G. And in plant number 2, we discover that this is an A and an A. So this is heterozygous, this is homozygous. And let's say, for now, that these two SNPs, or these two loci, are not linked. And let's say they're on different chromosomes. So here's another pair of chromosomes, here's another pair of chromosomes. So on this pair of chromosomes, this second SNP would be an A here and a G here. And this second SNP would be an A here and an A here. Right? Okay. So now when we do this cross, what we're doing is we'll take in pollen from one plant. Let's say it's this plant. Let's make this the male plant. And we'll take pollen from here. And the pollen that this plant can generate will always have one from number 1 and one from number 2. Yeah? So one pollen it could generate, one pollen grain it could generate will have a T and an A. And another one it could generate would have a T and a G. And another one it could generate would have a C and an A. And the last one it could possibly generate would be a C and a G. Yeah? 4 possible pollen grains, this plant. Yes? And then this plant, when let's say this is the female plant, so this produces the eggs. These eggs will look like this. They're gametes. From position 1, only C ever. And from position 2, only A ever. So then you will have C, A, C, A, C, A, C, A. So in the progeny plants, what you will have are these possible genotypes in the progeny plants. So let's say we have 100 progeny plants, and we look at them and we see, then what we can do is count how many plants have this genotype versus this versus this versus this. Yes? And if these two things are unlinked, that means this T is going to be found with an A half the time and a G half the time. And this C will be found with this A half the time and this G half the time. So in the end, there's going to be an equal probability that you'll have TA, TG, CA, CG. Therefore, if it's unlinked, let's make this unlinked. Yeah, we'll have, in the end, the progeny will be distributed like this: 25% with this genotype, 25% with this one, 25% with this one, and then finally 25% with this one. Yeah? Now, if these things were linked, what that would mean is they're on the same chromosome. And let's see what would happen if they were linked and on the same chromosome. Let's erase this. Do some erasing first. So now, if they're on the same chromosome, what that means is you would see, so if they're linked, what that means is position 1, which is here, it might be on this chromosome, and then position 2 will also be on that chromosome. So in that scenario, this T and C would be here, position 1, position 2. Position 2 might be here, and that would be, in this case, an A and a G. Yeah, and then on this side it would be an A and an A. So the way I got this set up, they're linked. T is linked to A, C is linked to G. So what that means is T and A would be found together more often. C and G would be found together more often. The only way to get T with G is to have a crossover. And that crossover would lead to a recombinant. And those recombinant classes in this case would be T and G and C and A. And these are them. This is T and G, and this is C and A. These are the two recombinant classes. And the sum of all these recombinants tells you the relative distance between these two sites. So let's say if we just look at all the progeny, and we saw that 5% of the progeny were TG and CA here, and let's say 5% were CA and CA there. Yeah, so those represent the two recombinant classes. And then the rest, so this is 10% of the total. The rest would be 90%. So we'd see 45% here, and about 45% here. Yeah, and if we see a distribution like that, that means the recombinant classes altogether make up 10%, and that means that the genetic distance between these two sites is 10 map units or 10 centimorgans. Yeah? So you can tell whether or not these two sites are linked by looking at the distribution of these genotypes in the progeny. And again, in this case, these two are the recombinants. We don't know, before we do all this, which ones are the recombinants and which ones are not. So basically what we'll have to do is look at the progeny and see if we see some kind of equal distribution among the 4 possible genotypes in the progeny. And if that's the case, then they're not linked. And if we see some kind of unequal distribution among the progeny, that means there's some linkage between the two SNP sites. And let's say we do a SNP discovery job and we find 1,200 SNPs. And I'm going to start writing them down. Let's say 1, 2, 3, 4, 5, 6, 7. And you'd have to ask the question, is 1 linked to 2? Is 1 linked to 3? Is 1 linked to 4? Is 1 linked to 5? And then 2 to 3, 2 to 4, etc., etc., etc. So you can see how this would be kind of a job best done by a computer and not by somebody like me. So what I'm trying to do now is try to figure out a way to automate this and make it happen with the help of a computer. So I'm hoping you can help me with that. Anyway, that's the problem we got right now. And let me just pause this. I just want to say, let's go back to that slide. And then, what we saw was the SNP number 1 was heterozygous for the first position, heterozygous at the second position. SNP number 2 was homozygous here at the first position, homozygous there at the second position. And I kind of think that's the only way you can get mapping done with SNPs. I'm not sure about this, but for instance, what if we take a second example where we have a plant and another plant, and then at SNP 1, and then SNP 2, SNP 1, SNP 2, and this time let's make this AA, let's make this GG, and let's make this CC, and let's make this TT, right? This plant will produce, let's say, pollen. That pollen will only be A and C, SNP 1, SNP 2, right? These eggs from this female plant will only be ever G at SNP 1, T at SNP 2. So this is the only genotype you'll have. And this, we won't be able to get any information from this because every single progeny will have this genotype. Yeah. So I think the only way to get mapping done is to have a situation where you have heterozygotes on this side, on one side, and homozygotes on the other side. Yeah, so I think probably the thing to do is just go through the whole thing with find all the heterozygotes in one parent and make sure they're all homozygous with the other parent. See if you can map them, and then determine whether you can find all the heterozygotes on this side and all the homozygotes on this side, and see if you can map those, and then see if you can generate a map that way. I am hoping somebody can help me with this. Anyway, that's it.